Hello everyone, you are welcome to clip 5 of part 7. Now we talk about 5G networks, and also we will introduce some concepts about the standalone wide area network. As we mentioned in the last part 4, that we will introduce for the fifth generation. We said that there are some limitations for the fourth generation, which was motivating engineers to go and operators to go to the 5G. And actually, the main reason, as we mentioned, is the industry needs. So in order to provide like massive machine type communication, to increase the reliability of communication, and also to achieve like very small latency or delay. So those are major requirement was limited in the 4G, so it was not possible to be achieved and satisfied in the fourth generation. So actually, the 5G requirement, which was set by ITU, was as following: that it should have downlink data rate up to 20 gigabit per second and uplink up to 10 gigabit per second. The spectral efficiency should be in the downlink 30 bits per second per hertz, in the uplink 15 bits per second per hertz. User plan latency for the single user and small packets should be 4 millisecond for the enhanced mobile broadband, and 1 millisecond for the ultra reliable communication, low latency communication. We will describe those later. And also, the control plan latency shouldn't be more than 20 millisecond. Control plan latency, it means that, for example, to maintain connection or release a connection, making the control signaling between the user and the network. Also, the maximum aggregated system bandwidth, at least the minimum is 100 megahertz. Remember that in 4G, actually, this was the maximum, 100 megahertz, but here it should be the minimum, and it should be possible to up to 1 gigahertz at higher frequency bands above 6 gigahertz. And also to support mobility up to 500 kilometers per hour, like, for example, the fast trains. So those were the requirement of ITU. And then, as we mentioned, 4G was not able to achieve that requirement. And one of the requirements is latency and also the reliability. And we described this in the previous part. So one of the most important results in the fifth generation cellular network is the ultra reliable low latency communication, which is known as URLLC system. So in this part, we will be able to deliver very reliable communication. It means that there is no discontinuity, with the probability up to 99 and 3 nines, 4 nines after the point, at certain latency or maximum latency. And of course, in order to achieve this 20 gigabit per second, it is only feasible for the spectrum, with the new spectrum above 6 gigahertz, because as we know that most of the band less than 5 gigahertz is like licensed, and it is crowded already. Of course, there are some technologies like cognitive radios. We will mention this in the next part. In part 8, we will talk about cognitive radios and how to like harvesting spectrum from that band. Yes, and okay, let us go to this very important actually figure. And in this figure, it is called the triangle of 5G. Here we can see that we can see the three corners of requirement. that or for of the main application or achievement. The first corner is very large number of supported devices, and we call it like massive machine type communication. Those that it can be small bandwidth, it can be low data rate, but we should be able to support massive number. Massive number, according to the requirement, is up to 1 million device per kilometer square. So you can see that it is really a huge number. So this is one corner, the massive mobile telecommunication or massive machine type communication, very large number of devices. What is the second corner? The second corner is high reliability at very low latency, and it is known as URLLC, the ultra reliable low latency communication. What is the third corner? Is very high data rate. Also, it is known as enhanced mobile broadband. So actually, those are the three corners of the 5G. And you can see around these three corners, we can see the different applications. Every application depends on the requirement. For example, in IoT, the Internet of Things, usually there are a huge number of IoT, and usually they don't need that high data rate. So you can see, because as you go up, it means that more data rate is needed, higher data rate is needed. If you go to this direction, it means that lower uh, latency or delay, and so on. So going here also, of course, means that higher data rate, and going in this direction means that larger number of devices needed. So here we can see the IoT. We can see here the smart city, for example. Smart city means that we will need very large number of devices distributed, but in the same time we need also some like throughput, for example, like security camera, for example. We need high data rate as well. And you can see here it is mainly for the mission critical application, self-driving cars, vehicular to anything or to everything communication. So here you can see that we need the latency is important. So it should be low latency, but it should be also high enough data rate in order to exchange information between vehicles or between cars, for example, on the road. As we go closer to the very high data rate, we can see, for example, 3D video, 8K definition video, and so on, and so on. Augmented reality. We can see here in the middle this VoIP. So VoIP doesn't need that high data rate, but it needs low latency, and in the same time, we should be able to support all terminals. So it is in between high reliable and massive number of devices. So actually, according to this triangle, so we can see the other corners here, the corners, and also the applications around this one. So this is important in 5G applications. Um, how to achieve this requirement? Actually, we have two parts. The first part is the radio interface. Always, this is the most critical part, of course. And the second is the core network. Let us first talk about the new radio. Is known as a new radio. Actually, we mentioned about this before in the in previous part when we talked about multiple access or modern communication techniques, and we mentioned about this NOMA, non-orthogonal multiple access, and we mentioned why it is important there. So the new radio actually modulation and multiple access named is a non-orthogonal multiple access, and also it uses massive MIMO technology. So massive MIMO means that we use very large number of antennas at the transmitter and at the receiver, and it is possible to be used when we use very high frequency. For example, if at 30 gigahertz of frequency, the wavelength lambda is about 1 centimeter, because the wavelength is the speed of light divided by the frequency. So the speed of light is 3 times 10 of the power 8 meter per second. Frequency is 30 times 10 of the power 9. So you can see that here that it will be about 1 centimeter. And we know that in MIMO antennas, that the distance between antennas can be about lambda over 2, for example. So it means that we can achieve about if we have antenna with zero point 0.5 meter times zero point 0.5 meter. Okay, within this area actually we can install about 10,000 antennas if you keep the distance between them like zero point 0.5 centimeters. Of course, we have many other like problems like mutual coupling and so on. So even if the number is much less, even if we talk about like 200 antenna or 300 antennas within at the base station, it means that we have massive number of antennas there. So and also in the user equipment, within 3 by 3 centimeters actually you can like install maybe 30 antennas or 36 antennas. Then of course this MIMO or massive MIMO antennas is one of the of recent technologies which can achieve that very high like separation between users, and it can improve the quality of communication and increase the spectral efficiency. Uh, Yes, and as we mentioned that the one of the major challenges is how to support massive number of terminals. Actually, if we start to think about supporting like 10,000 IoT device in one base station, then it will be really a big problem. If we think about 3G, for example, because we have limited number of spreading codes there, and if we talk also about 4G, still we have limited number. Yeah, we have much larger number of subcarriers or subbands there. So and also we can use like space-time coding, multiple antennas and so on, but still it is not up to the level to support tens of thousands pair of devices within one cell. um, uh, because of the limited number of the subcarriers. And also there is another problem. Even if we provide a new like RF with very large number of subbands that it can provide the enough subbands for, or the required number for IoT, we still have one critical problem, is that usually in normal like 4G or off-DM communication, usually they should be like synchronization in order to keep the orthogonality between devices. So we should, for example, allocate certain number of subbands for each terminal in the uplink, and then we have some synchronization in when they send their messages, so that we can keep the orthogonality between them. If we miss this, then we have some, for example, inter-carrier interference between the subcarriers. So in the 5G, in order to minimize the latency, we should provide with the grant-free access. So the IoT, the or the sensor device, it should transmit the data wherever there is something to be or event that they need to submit, but without the requesting for the access to the network and spending like long time to set up the access. So as we saw before that the control latency, it can be up to 10 millisecond actually. So if every time the sensor wants to establish a connection to the network, then they will like lose 10 millisecond every time. So in order to handle this problem, then we should have this access, grant free access, so the IoT can transmit wherever that they have data. But the problem that we will lose this orthogonality between like subbands. And because of those two things, two problems: the number and also the accessibility. Then we have to use non-orthogonal multiple access. And actually, as we mentioned also before, this non-orthogonal multiple access is not new. So we use, for example, in the 3G, we use this CDMA system, and CDMA, even if even they are orthogonal at the transmitter between different users, but we cannot guarantee that they will be orthogonal at the receiver. Okay, and uh, okay, so this NOMA has been adopted at least in the first version of the new radio of the 5G. Okay. How can we deliver or decode the signal if they are not orthogonal? Of course, when they are not orthogonal, there will be interference between two different signals, and because of that, we use, for example, power domain NOMA, and in the power domain, that we allocate different power for each user, and we guarantee that the power at the receiver should be different at the receiver side. And because of that, for example, if the stronger signal, for example, this is U2 is the strongest signal at U1, then the U1 actually they start by decoding U2 signal, and after that, once it is decoded, then it can be subtracted from the received signal and then decode U1 signal. So it is called like a successive cancellation procedure. So start by the strongest signal. We decode it first. Once it is decoded, then it is used to remove it from from the received signal. Then we will have the only the other or the U1 signal with the additive noise. Of course, in case that we have multiple users, then the same procedure will be repeated. So we have it is for this reason it is called sequential interference cancellation. So every time that we cancel one of the strongest signal, the second strongest signal, and so on. Okay, and actually we have some other kinds of how to manage this non-orthogonal multiple access, like spatial assistant. So with the spatial, as you can see here, that using multiple antennas, then we can separate between different users with these different beams by using radiation pattern, by using this beamforming. So by using this one, we can also minimize the interference between different devices in the uplink and also in the downlink. So spatial domain non-orthogonal multiple access can be very useful for fixed located IoT. We know that we have some IoT, like they are not every devices they are moving. So in some application that those devices are fixed and located in certain place, in that case the base station might just allocate the beam because they use, as I said, that for example, massive MIMO. If they use high frequency, then they can allocate certain beams for different IoT, and then it can minimize the interference coming from every group of devices. And for those which are in the same beam, it is possible to allocate different bunch of subcarriers, so that they can use that to guarantee that they are orthogonal, but the same set of subcarriers can be used from the other beams as well, or patterns as well. So in that case, we can reduce or minimize the interference between those. We have also the code domain non-orthogonal multiple access, where the signal is not transmitted over the subcarrier or over the subband as it is, but we spread it with some spreading factor, with some like direct sequence CDMA, and in that case we can also reduce the interference, even they are on the same subcarrier, but because they use orthogonal codes, then we can reduce the interference among them. However, of course, the cost of that is the reduction in the in the throughput, the reduction in the throughput. Or we need, because for these subbands, for example, if we assume that we can also transmit up to 15 kilobit per second per subband, then this will be fixed. So if you use, let's say, splitting factor of 1000, then it means that you will be able to send bit rate only 15 bits per second. So of course it is very small, but 1000 is very large as well. So if we say that we want to use splitting factor of 100, it means that you can send up to, let's say, 1 point, is it 1.5 kilobit per second. Yes, so it is 1.5 kilobit per second of data. So one needs to compromise or to trade off between the interference and also the required data rate. So major advantages of the 5G new radio are achieved by including much higher bandwidth than the 4G. So the bands are divided into two ranges, like we call them like frequency range 1 and frequency range 2. Frequency range 1 including all frequencies from 410 mega up to 7125 megahertz, and the frequency 2 range, which is at the millimeter wave, it is from 24.25 gigahertz up to 52.6 gigahertz. However, of course, not all bands are used here and here, but we just making like aggregation. So we try to all the time find any white spaces or not used spaces in order to include them in the standard. Here you can find in the slide some like explanation about the development of the releases of the 5G, starting from the release 15 to release 16 up to release 17, which is now the current release. Release 18 is a candidate release now. If you go to the 3GBB, you can find the more description about the development of those releases. But actually, to save time, I will drop this one. We have spent already 5 clips in this part, and should it be more? And yeah, so now we come to what is the improvement done in the core network. So we saw the improvement in the radio part. In the core network, it has been also some improvements, and maybe the most important development or improvement in the 5G core network is the concept of virtualization. Yeah, so in virtualization and modular network based on virtualization, it gives the possibility that part of the functions done by core network, it can be moved to the cloud. So in the cloud, that cloud network or core network can be moved to the cloud and making or get benefits of using cloud computing. And this actually makes it reduce the costs of the core, and also makes it distributed core. And actually it can be the hardware can be shared by different like operators. So not necessarily that every operator must build its own core network. So the core can be shared among different operators, even from different countries. Of course, it is still in the first stages. It is still in the beginning. It is many of these are just ideas or under discussion, because we have many other like constraints, not necessarily technical, but related to some regulations, for example. But still, at least from the technical point of view, it is possible to have shared, and for example, companies or operators can just rent some of the computing capabilities available on the cloud, and to move part of it is like core network over that cloud. So here we can see the major elements of 5G network. So for example, the mobility management entity, it was in 4G. You can see that it has been distributed over in two functions. The first is called access and mobility management function, and the second is called session management function. You may ask why we divide this MME to two different logical functions here. One of the reasons is that we are looking for which part that must be in the node B, for example, on the base station, and what part we can move it to the like modular or making it with the virtualization or move it to the cloud. So engineers start to think how to distribute or uh, not distribute but divide some logical functions into multi-functions, and we know that this part should be there and this part could be on the cloud. This part must be like implemented in the node B on the base station, but this part can be implemented in the cloud or over some computing device somewhere. So this was the concept here. And also you can see that the packet gateway or the serving gateway, it also has been like now different names, like in the session management function. It takes care of that as well. And you can also see that the some other functions related, or the new 5G functions, like the NSSF, which means that network slice selection function. And actually, for the network slice selection function, helps in setting up multiple virtual network slices of the radio access network, and transport the network to meet a specific service requirement. So this could be done by this NSSF. So this is the reason that it is a new 5G function, because it provides the visibility for this virtualization and divide or slice the functions over different functions. Okay. And then we have also the network exposure function here, and we have the network repository function. And everyone, actually, they are mainly useful for the pushing some of the functions to be done in the core network to external network entities. Okay. And actually, not only in the core network, also in the node B, there has been like major changes in the base station. In the 5G, we call it like next generation node B. So it is 5G J and B, means that next generation node B. And here also you can see that it has been divided into two paths. It is called, for example, or it has been split actually into two paths. It is called centralized unit, JNB centralized unit, and JNB distributed unit. Again, the same concept that I mentioned, that we need to know which part should be implemented by the core or by the operator, for example, in the node B, and which part could be moved or pushed to the core network. And you can see here that we have the JNB distributed unit mainly for the radio functions. It means that for the physical layer, for modulation, demodulation, for example, computation of the signal quality in order to select the modulation level. For example, is it 64 QAM, 128 QAM, or 256 QAM? Also, it can manage for the coding and decoding some functions of the MAC layer. It should be done at the node B. So everything related to the radio, to the physical layer, and few functions of the MAC layer must be done in the node in this next generation node B in the distributed unit. The other parts, for example, it is shown here, transfer of user data. Of course, we know that, but mobility control, radio access network sharing, positioning, session management. All these things should be done at the central unit. So it is GNB central unit, but the central unit, as I said, it can be like shared with other operators, and it can be also moved to some or part at least of the function can be done in the cloud. Here we call it like hall is the connection between the node B's or distributed unit to the core unit. Okay, now we after this very brief and very fast introduction to the fifth generation, we come to the question: what is the main benefit and main disadvantages of using cellular network? Cellular network is already installed network, and it has, as we can see, or as we saw from 5G and 4G, we saw that it provides high reliable and very like stable and mature links for companies for to be used, for example, in their industry and so on. However, there is always two disadvantages or problems for companies, for big companies, to use the cellular network. First is related to security. Of course, operators, they provide highest level of security as well. So we have, for example, in this SIM card, we have also the keys is there for which is used for the security tasks and operations, to make like confidential like access to the network, or to check for the encryption and the decryption. And it is not that easy to fetch this keys from the SIM card. And also, to get them, one needs to have physically come to that part, which is not, of course, possible in some critical applications. However, still, it is in the network itself is accessible by millions of people. And even if the operator provides some virtual like limitation or protection, but still some companies, they don't like to provide or to use this third party solution for their own like vital application or very critical applications. Okay, this is one disadvantage. The second disadvantage of using the third party is the cost. So the cost is always can be issue. Of course, if you want to get SIM card to connect like 5 or 10 or 50 or even 100 modem to deliver your data, it is doable at reasonable price. But for some application, for huge or massive machine type communication, if you have like tens of thousands of devices that you need to get like data out of them at a regular basis, or used for to send control signals or some or monitoring signals. So such kind of tens of thousands, of hundreds of thousands, it will cost some money. So even with a special deal with operators, it is still very expensive, especially if you requested some like special contract, for example, high secure or static IBN or the static internet protocol address, for example, and so on. So these can be very expensive. And what is the option, or what is the other solution for companies to solve this problem is start to using standalone wide area network. I should say that even the standalone concept has been now like many years with us, like Bluetooth is one, and also the Zigbee. Okay, like Zigbee also is another sorry. Zigbee also another standard, and also we have maybe this nowadays this ultra wideband and many other solutions. And actually, near field communication, we have RFID. So we have actually many solutions which they are standalone. You can just use it yourself. So you don't to have license, or you don't have to have anything from you might use your Bluetooth device without making any contract with anyone. So they are standalone solution. But what is the problem of these all these solutions? Also Wi-Fi. I shouldn't forget this Wi-Fi. So all these solutions, they are standalone solutions. But the common problem with all these solutions that they are either short range or medium range, but they are not wide area network. They cannot be used for like if you want to cover like 5 kilometers or 10 kilometers of data. This is one major problem that for these solutions. Why? Why we cannot provide it for long distance? The main reason is that all these solutions use this free bands, which is called, as we know them before, ISM bands. So those are free bands. Free bands means that everyone is allowed to use it, but at the same time, it has high interference, very high interference in that bands, and also um, um, the propagation behavior, especially for those ISM bands around 2.4 gigahertz, the propagation is not that good at that frequencies. And in order to transfer to make long distance communication, you will need to use high power, because those solutions are low distance solutions or short range solutions, so their power is always limited. So for example, some of them only zero point 0.1 watt, and some of them even less, that like zero point zero 0.01 watt, like one or few milliwatts is allowed. And this is enough actually to cover like 5 meters or 10 meters. But of course, it is not enough if you want to cover, for example, 5 kilometers or even 10 kilometers. And how this problem has been solved or has been handled, there's now a new standard or new technologies come to the market. It's called a standalone WAN, and those they use lower ISM bands. So they use, for example, frequencies around 900 megahertz in US and around 800 megahertz in Europe, because we have also some free bands in ISM bands or license free bands in around these frequencies. And around these frequencies, the propagation behavior is very good. And also they can use a power up to 1 watt. And one of the solutions actually is called long range WAN. This is one of the standards, and we can see some of them later. Okay. So we have here, I just bought 3 solutions available now. This is long range WAN, and in this long range WAN, it can support up to 20 kilometers under like a certain condition. And actually inside city they said that it is about 5 kilometers only, and it is a good option for IoT with a low data rate. Actually the data rate can be 27 kilobits per second if we use the frequency shift keying, but in practice it is less than like a few kilobits per second. Actually this 27 kilobits per second, it can be in very strict conditions, but in reality it is few kilobits per second that you can achieve with this long range one. And also we have other limitations, as we will see them later. And also we have this signal fox or sigfox, and it is low cost, low power, a very low data rate. Actually the data rates can be only 3 bits per second, but it can cover very large area up to 50 kilometers, and it is perfect for low rate and event based IoT applications. We have also wave IoT. So it is one of the machine-to-machine application. It can cover up to 30 kilometer in a rural area, and it can support data rates from 50 bits per second up to 25 kilobits per second. So those technologies are already now engaged new in the market, and there is also some standard now is going. The standard is already there, but there are always some like improvements. Like for example, IEEE standard for local and metropolitan area network. It is named as 802.15 for G, and also we have this LoRa Alliance. It is called LoRa Alliance. So you can check it on the internet to see about this alliance, about this many companies they are shared in that to put some like common standard for that. It is like Bluetooth, for example, like the Bluetooth, because right now what I read about this LoRaWAN, that there is some incompatibility between some devices because they were like manufactured by different like vendors, and then they have different characteristics in the radios, which means that they cannot work together. So this, of course, this will be a problem, but it is expected with the new technology comes to the market, and since they use this license-free bands, which means that they try every company to use their experience to improve the quality of the transmission and reception, but this might sometimes make problems in the intercommunication between those devices which come from different companies. But I think they will go to converge to like some standard about this. So this, as I said, that most of them they use frequencies less than 1 gigahertz, like in 802 up to 9 to 8 in megahertz in USA. This is a free band, and also 863 up to 870 megahertz in Europe. This also a free like or license free band. And the power level, it can be the maximum allowed power is about 1 watt. Using some of them also they use some directive antennas to enhance the distance, the coverage distance. Yes, this is now a little bit about this LoRaWAN uh, WAN. So it is long range wide area network. As I said, that they use this license free in industrial, scientific, and medical ISM bands. The modulation concept using in this LoRa technology is CDMA. So they can separate between users by using spreading code, the orthogonal spreading codes in the uplink and in the downlink, and also between different devices. So each device connected, or each IoT connected, it can be like augmented with this orthogonal code. So actually we have different every device, it might have like many number of orthogonal codes. It is called golden codes. You can generate like billions of them in one device. It is not difficult to produce them. And then the gateway can inform that each device, we have one control channel. Over this control channel they can inform the device to which that code or spreading code they can use to guarantee that there is no interference between different devices. However, as I mentioned before, that in the CDMA we cannot guarantee the full orthogonality between devices, and in order to minimize the collision, that each device shouldn't send more than or use the channel more than 30 seconds per hour. So every device, it has 30 seconds that they can transmit per hour. And I read one paper actually. They make some simulation, intensive simulation, and they found that even this with this condition, the probability of collision was very high. Even with this collision, of course, when you are talking about thousands of IoT within some area, then even with this condition is not enough. And they said that they got good result if it is allowed to use like maybe 30 seconds per one day. Now I don't remember exactly what was the recommendation in that case, but anyhow, in some applications, for example, if we have smart grid, and within that smart grid we have IoT devices, and those IoT devices, they don't need to transmit all the day. So, for example, if this certain event happen, then they will send the message in that case only. So, in that case, in some application, so it might have some good applications that we can use. For example, if you have card reader, and the person that he has the card, so they will send a few packets if they just touch this card reader to the, for example, to the taxi driver or to the bus driver. So when you come in, so just touch this card to the reader, then it takes maybe 1 second, and then that's it. And looking to this one, how many time that he will ride, for example, buses per day, maybe one time, two times, 5 times per day. So this reader can be used, or can use the channel like 5 seconds per day, not even by hour, or 10 seconds per day. So actually we have some applications that they don't need that intensive or continuous to be in communication. So we need to think what kind of application that this data could be, or this technology could be useful. Here, I found few of those applications, like collecting data from distributed climate and weather sensors, checking and control of automatic gates and doors, collecting online data from sensors distributed in farms for agriculture or animal barns, deployed to track taxis, cars, and street lighting, as well as traffic control, monitor the status of parking spaces over the whole city, reading utility meters. So there are few of those applications that we can use with this LoRa technology. So thank you very much for attending this part 7. So in this part we covered the wide area network and some of their applications. Mainly we went through the cellular network, starting from the GSM to the third generation, to the fourth generation, to the fifth generation. I tried to be as brief as possible, in the same time to give you some insight about what happened between generation to generation, and also how to select the proper technology for the certain tasks. And finally, we saw this standalone wide area network. This standalone wide area network, in my opinion, is still in the beginning, in the first stages now. Maybe it has started a few years ago, and I'm sure that they will be developed more and more. And maybe it will be at certain, or at some point it will be part of also to the 5G, because I forgot to mention also that 5G is not only this technology, because one of the motivation, or one of the philosophy behind 5G, that it should include all other communication technologies. So for example, 4G is part of 5G. Narrowband GSM will be part of 5G. So the idea that 5G that should be very flexible in order to include any other technology. But anyhow, we heard now about also the 6G, and they said that if the 5G was directed to the industry, and then the 6G should be directed to the intelligent systems, or standalone systems, or they call it like smart systems. So smart systems, in order that it comes to the cognition level and the decision making levels, they will need different kind of communication. And they said that even the communication itself. So how it works, that the algorithms, how the algorithms work in telecommunication, they will be based more on the AI, the artificial intelligence, and machine learning. So this was the, at least now, the trend of the sixth generation, and including more about this visible light communication, including more about the using the for example CubeSat and other technology that we are going to briefly discuss them in the next part. Thank you very much, and see you in part 8. Thanks.